Hello, my name is Henry Förster, and today I want to talk about compact RAC drawings. This talk is based on a joint work with my advisor Michael Kaufmann. And of course, first of all, I should define what I mean by drawing. So I mean a graph drawing, which is an embedding of a graph in the plane. So as you probably know, a graph is consists of a set of vertices V and a set of edges E, and then you embed the vertices as points in the plane, and the edges as open Jordan curves that connect the corresponding endpoints. So drawings can have several properties. For instance, they can be planar if there's no intersections. They can be polyline with k bends per edge. In this scenario, there's at most 2 bends on each edge. And they can also be straight line if basically you have a polyline with 0 bends. So in addition to planar graphs, one has also considered beyond planar graphs, and this is based on the following observations. So there's many classic results for planar graphs. Like, for instance, already Euler has shown that the density is at most 3 n minus 6 edges. And there's also efficient drawing algorithms. For instance, you can always draw a planar graph in linear time, straight line in quadratic area. However, many graphs that we encounter in practical applications will not be planar. For instance, you could be given such a graph, and as you can see, if you just use some random placement of the vertices, it can look quite terrible. However, very often you can still create a drawing which looks relatively nice, or these two drawings show the same graph. And then, of course, you may wonder what is the properties that make this drawing better than the other one. And basically there's two nice properties that we see here. So there's a few crossings per edge. This is captured in the literature by the model of k-planar graphs, where you allow at most k crossings per edge. And then you can also see that there's large crossing angles, which have been also shown in empirical studies, as referenced here, to contribute to a good readability of the graph drawing. Finally, there's also results that indicate that few bends per edge are helping to understand graph drawings, and these latter 2 points are captured in the model of RAC K graphs and drawings. So in a RAC K drawing, you have that all crossings appear at right angles, and there's at most k bends per edge. So now, of course, you may wonder which graphs can I draw with k bends, so that all crossings are at right angles. And there's quite restrictive density bounds for these graph classes. In fact, if you allow no bends, you can have at most 4 n minus 10 edges in your graph. Similarly, if you allow 1 bend per edge, you can do slightly more. So you can do 5.5 n, and the additive constant can be between 11 and 72. We don't know the exact value. And with 2 bends per edge, you may wonder if you can do much more. However, probably not. So the upper bound that is known as 74.2 n, whereas the lower bound is 7 and 5/6 n. However, probably it's much closer to the lower bound. And now, of course, you may wonder what happens if I allow 3 bends per edge, and very surprisingly, suddenly you can do all graphs which have even a quadratic number of edges. Now, of course, you may wonder if I can do all graphs with 3 bends per edge, so that they have a RAC drawing, how much area do I need? Which would be another property that maybe would be good to keep low. And for this purpose, we will place vertices and bends on the grid, whereas the crossings can also occur off the grid. And there's in fact some known results for this problem of how much area do you need, and the first drawing algorithm for the complete graph with 3 bands per edge gives you quartic area. This was then improved for the scenario where you have 4 bands per edge to cubic area, and very recently to n to the power of 2.75 for 6 bands per edge. In contrast, the known lower bound is simply this quadratic area, which comes from the fact that your graph will need to have some bends in its drawing, and this will be a quadratic number of bends that you must place on the grid as discussed before. And now I will go over our results. So the first one is that we can do cubic area with 3 bands per edge. So how does it work? Well, first of all, we will place each vertex in some disjoint region. Namely, we assign these gray colored square-shaped areas for each vertex. And now we will create basically 2 types of first segments that are incident to each vertex, namely n-I of the green bands which appear at the right side of our square, and I-1 bands at the top side. So we will refer to these segments that connect the vertex to have these bands as the start segments. And now we attach middle segments of slope n-1 at the right side bands. So you see it's basically almost like a vertical line, and then we complete the drawing with middle segments of slope -1 divided by n-1. So basically the red and the green segments are perpendicular to each other, and we see that this creates a connection between each pair of vertices. So the resulting drawing is a RAC 3 drawing in cubic area. So when we started to study this problem, we believed that probably cubic area may be the truth, like this is the minimum area that you can hope to achieve. However, then our second result that we found was that we can do 8-band RAC drawings in quadratic area. And that we do as follows. So first of all, we insert our vertices on a common diagonal of slope -1, as you can see here. And then we attach basically to each VI the start segments, and we do that so that their bands are located on the diagonal of slope 1. And those diagonals are parallel to each other, so the start segments of different vertices do not interfere. And now we can route our edges with segments of slope 2n-1 divided by 2n and -2n divided by 2n-1, which are the green and the red colors respectively, so that we arrive in this middle region where suddenly everything stops. And now we have drawn something which we will refer to as half edges. And by matching our half edges without intersections, we can create a connection between each pair of vertices exactly once. And this gives RAC 8 drawing in quadratic areas, so the width is like 12n and the height like 8n or 10n. And this planar matching, of course, is the most tricky part here, and I will discuss how to do that next. Namely, first we consider how we can see basically the top left bands in this region from the bottom right bands. There you can see it follows basically this line that with the arrows that I've drawn here. And this gives you an ordering where you encounter a band which is incident to each vertex once, and then you encounter the same sequence again. Now we have to create a matching between these two orderings. So basically the bottom right bends can be seen in the same order from the top left side. And we do that by saying first we create one edge of span 1, so we go from blue to red, which are directly incident in this ordering. Next we create two edges of span 2, so green is 2 away from purple and orange is 2 away from blue, and those are the two segments of span 2. And then this pattern repeats, so we get 3 times span 3 and 4 times span 4. So now, of course, you may wonder, is this really all connections once? And this is in fact 2. And you can see that because the span n minus I corresponds basically to the span minus I. So what do I mean with that? So if you look at the span 1 edge, so the blue goes to the next color in our ordering. So we go from blue to red. Whereas if you look at these span 4 segments in the end, there basically we go from green towards red, which are also consecutive. However, the green succeeds the red in our order. And as you can see now, this sums up to 5 times the span. And then we can show the correctness by an inductive argument. So we remove the ones with span I and span I minus 1. And we see again that what remains is basically a cyclic list, which starts in this case at green and at red. So we have again some constant times n of bands, and we don't skip a color. And now we would just show the planarity. So here basically the argument is that we have short spans of edges in general, and you can see in the top right illustration that basically all the matching edges that start at this bottom right spoke, the second bottom right spoke, are completely located in this brown shaded region, and this is basically guaranteeing planarity. Okay, so while we already have shown that we can do cubic area for RAC 3 drawings in general, we can even do a bit better if our graph is p-partite, and then we can do p to the power of 4 times n to the power of 2 area. I will discuss this next. So if you want to do that, first we augment our graph to the graph k and pp. What does it mean? So we have a p-partite, complete p-partite graph with np vertices in each partition. And np is basically the number of vertices in the largest partition of the input. And now the approach is basically quite similar to the other two algorithms that you have seen already. So we insert vertices this time per part on a vertical column vertical. And now we insert start segments that will go to the following parts. And those will occur on a common slope of 1. So here you see also that they are already grouped a bit. You can see in the left part of the drawing. The first 3 each time go to the next part, and the next 3 will go to the following part. And basically we do the similar thing for the start segments, which will go towards the prior parts. And now we connect our segments with these segments of slopes p and p minus 1 divided by p and p, and this perpendicular slope. And this gives us a RAC 3 drawing in np p square area times np times p square area. Okay, so we have seen quite some upper bounds now, and now you may also wonder if we can do 8-band in quadratic area in general, and we can do with 3 bands in quadratic area if the graph is p-partite. Why is it not just easy to create also a RAC 3 drawing in quadratic area in general? And we give an argument that this is actually not possible. And for that, we first introduce some properties that hold for such drawings. So for RAC 3 drawings, it would fit in quadratic area. First of all, there will be some sets of parallel segments S and T, where the segments in S are perpendicular to the ones in T, so that each of these have cardinality n square, which you can actually see in all of our constructions. So the green segments, let's call them S, are perpendicular to the red segments, let's call them T. And the proof for this statement utilizes the crossing lemma, which states that the drawing of Kn always contains at least n to the power of 4 intersections. So another nice observation that we will use is we only have n square segments, and now we basically sort the segments into sets Si and Ti, so that only the segments in Si are perpendicular to the sets in Ti, and we sort them by size. So set Ti is at least as large as set Ti plus 1, and set Si has at least as many segments as set Ti. And the largest one S0 and T0 will be our segment sets S and T that are in the statement. So now we can make some estimate on the number of crossings. We can make an upper bound for the number of crossings. So basically each of the segments will contribute at most S times T intersections, so each segment can cross the segment in the other set. And we can write this in particular so that we separate S0 from the rest. And we can also write the cardinality of S0 as Sn square, where S is some value smaller than 3, and it basically counts how many segments you assign to either set S, minus the sum of the remaining S segments. And now you do a bit of math and you see that the number of crossings is Sn squared times T0 minus something which is larger than 0. So basically the number of crossings is determined by the size of T0, and this must be n square, and by the assumption that Si is at least as large as Ti, we also get that set S has at least quadratic number of segments. Now, a nice property of these S and T segments will be that you find edges which have both of these segments. Namely, you find the quadratic number of edges which look like this illustration at the right. So you have your two start segments, and both middle segments are green and red. So they belong to S and T. Again, this is a property that you will see in both of our upper bound constructions for the 3-band setting. And to show that, we also consider the set of edges which contain middle segments from S, so they have a green segment, but not from T. So the second middle segment has some other color. And now we look at the graph that is induced by all these edges that have a segment of S. So it has a quadratic number of edges. By the crossing lemma, it must have n to the power 4 crossings. And then we look at two cases. So how can it be that it has n to the power of 4 crossings? So either the set which contains both segments of S and T, which can intersect, has quadratic cardinality. Or there must be a pair of segment sets S prime and T prime, so that there's many edges which have a segment from S and a segment from S prime, and many edges which have a segment from S and a segment from T prime. In this case B, however, we can look at the graph that is only consisting of the edges that have an S and S prime segment, and then you have still n to the power of 2 edges. However, it's not possible to have n to the power of 4 intersections because all the middle segments cannot intersect each other, and this inevitably creates some issues. So the correct case is case A, and the statement follows. Now, in the next step, we looked at some geometric properties finally. Namely, if you have width W and height H of your drawing, and the slope of the segments in S is P divided by Q for some co-prime integers P and Q, then we can show that H, W, and the maximum of P and Q is linear in N, which you can nicely see in this RAC 8 upper bound. Namely, here you actually see that basically the green and the red segments go basically through the entire drawing. And also height and width are both linear. And the argument here is that the crossings from S and T are located on a fine grid that is defined as follows. So basically the segments in S can start at any vertex and they follow basically the slope, any vertex of the normal grid, and similar the red segments follow the red grid lines, so they go through at least one of the grid points of the original grid. And now you count how many grid points you have, and this fine grid must have n to the power of 4 grid points to accommodate all the crossings, which can only be the case if these properties hold, which is something I don't want to go into too much detail because it's some boring math. Now, based on this, it's possible to subdivide the drawing area into square-shaped regions of side length max P and Q divided by half. And what this does is the following. So you can see this in this small illustration to the right. If you have ST edge, it will have its S endpoint green in a different region than its T endpoint, which is the right square. And this property we will now use, and we will show that basically if you look at the S points of region R, then it's mostly incident to some vertices that have no connection to the T endpoints, which you can see very nicely in this bipartite upper bound construction. So basically the green edges, green segments at the bottom left all go to the left vertices, and none of these vertices is incident to any of the red squares. Okay, so how do we show that? So let's look at the region that is bounded by the region R, and these two attached rays that go off with the angle close to the small angle. And now you can have basically 3 cases. So it could be that your vertex is located entirely in this region, then we call it an S vertex. It can be that it's outside of this region. And here basically we observe the following. So if you are outside of this region, then you must see the S endpoint inside the region. And you can do that only if there's a way going of your S endpoint, so it doesn't touch any of your S segments. And yeah, so you use the same angle as you see here, and if you choose the angle correctly, you can maintain that the distance between each of these rays is constant, and since the height of the region is linear, there can only be a linear amount of these rays, which gives you the number of connections to what's the green points. And finally, your point can also be inside this region where all the edges go that go from your region that is attached to the green segments towards your region that is connected to the red segments. And here we show that the bands attached to those vertices have distinct y-coordinates, which also gives you a linear bound on the number of bands that you can attach to such vertices. And based on these observations, our main proof idea is the following. So either we have loads of these segments, the edges that have S and T segments, then we must find a region with many of such edges, which comes from the fact that you have only a constant number of regions. And the S vertices that are incident to vertices bands in this region are not connected with each other via the S endpoints, which is a consequence of this fifth point. And then we basically consider the subgraph that is induced by the S vertices and repeat until the second property is violated, which then shows that there's a click in your graph that has not enough ST segments. Okay, so this is basically the current picture in the literature. And now I will state some open problems. So how many bands per edge are necessary for quadratic area is the most obvious question. So we have shown that it cannot be done with 3 bands per edge, and it can be done with 8 bands per edge. Maybe you can slightly adjust our proof to get it to 7 bands per edge. And also the lower bound may be extended to show maybe like 4 bands per edge. Again, connect to the lower bound, we may ask, is cubic area optimal? You could try to use our technique to show something stronger. And another intriguing question is whether quadratic area is possible in simple RAC drawings. So in a simple drawing, you are not allowed to have 2 edges incident to the same vertex intersect, and you're also not allowed to let 2 edges intersect twice, which are properties that are not guaranteed by our algorithms in any way whatsoever. Yeah, so this was all that I wanted to say today. So thank you for your attention, and have a nice time with the remaining videos of this conference.